Hello everybody, welcome to CS560 Algorithms and Their Analysis. My name is Yang Xu and I'm the instructor for this course. I'm recording this video because I'm currently in China and I've been waiting for my visa back to US for several weeks. So I'm afraid that I cannot come back in time for the first lecture. And if hopefully I get my visa next week, then I will no longer need recording more videos for future lectures. Because it's my first time teaching a course in video talk, and I'm not quite used to speaking to a camera while playing the slides and without seeing my own face. But I will do my best. First, let's have an overview of the structure of the whole course. This is a 500 level course, and maybe to many of you, it could be a very first analytical course in the curriculum of computer science department. And the learning goal of this course are as follows. First, after this course, you should gain a deep and comprehensive understanding of different families of algorithms, including the divide and conquer algorithm, greedy algorithm, graph algorithm, and dynamic programming, and so on. Second, you should understand the techniques that are commonly used to analyze the performance of different algorithms. For example, the asymptotic notations, which is frequently used to analyze the time and space complexity of algorithms. Third, you should be able to use pseudocode to implement algorithms that are directly covered or related to the algorithms introduced in this course. And in this course, we emphasize a lot on know-how. By that I mean towards the end of the course, you should be given a problem in the real world. Then you should be able to know the existence of different solutions to those problems. And among those solutions, you can choose the optimal one. You can choose the best solution that use the most efficient algorithms. And there are two prerequisites on this course, which is CS310 data structures and Math 254 linear algebra. And actually, as you will see as we enter this course, many of the topics in this CS560 will be an extension of some of the topics introduced in data structures. For example, you will go through the tree structure, the graph data structure a lot in this course. You don't need to buy a textbook for this course, as all the lecture slides are sufficient to cover all the topics. But if you are interested, these following two books will be very helpful to help you understand most of the topics, especially the first one, the Corman's book, Introduction to Algorithms, published by MIT Press. And this is the book that the majority of the course slides are based on. And I think reading the first book would be particularly helpful, and it gives you more details that go beyond most of the slides. And as I have seen that most of the students, most of you guys are from the Department of Computer Science, so you must have some prior knowledge of programming languages. But in this class, no prior knowledge on any specific programming language is required because I'm not using the syntax of any specific programming language, for example, Java or Python or C, C++ to describe algorithms. And actually for homework assignments and midterm exams and final exams, all the questions are paper-based, and all the answers that are also, you also just need to write down the answers on paper, and there's no programming-based assignments or exams. And as I just mentioned, that we don't use programming language, a formal programming language, to describe all the algorithms covered in this course. Instead, we use pseudocode, and we will come up with a pretty well-defined syntax of pseudocode, so that when you are you're doing your homework, you can use a uniform pseudocode syntax to describe the algorithms. Okay, so here's a bit more information about myself. I'm an assistant professor of computer science at SDSU, and my research areas include natural language processing, computational linguistics, machine learning, psycholinguistics, and cognitive sciences. And if you're interested, you can visit my website here. Okay, so now let's enter the main part of the first lecture. In this lecture, I will go over the definition of algorithms, the common problems that various algorithms are applied to, and finally, we will have a brief review of the mathematical backgrounds that are required, that are necessary to understand the topics in this course. So, what are algorithms? According to the definition in most textbooks, algorithm is defined as a computational procedure that takes some inputs and produces some outputs. So we need to have some computational problems at first, and then we'll develop an algorithm as a tool to solve such a computational problem. Okay, so the problem itself, the computational problem itself, can be specified as a relationship between some inputs and some outputs. And then the algorithm describes a procedure or some operations for achieving or for characterizing such a relationship between the inputs and outputs. And we can look at a concrete example here. So sorting problem is one of the most common computational problems that we will encounter in computer science. So this problem takes a sequence of n numbers as its input, for example, from A1 to AN. And the desired output is a permutation of the input sequence. That means the reordering of all the elements in the input. So the output is now A1 prime, A2 prime to AN primes. Okay, but all the elements in the output should satisfy that A1 prime is less than or equal to A2 prime is less than and equal to A3, blah blah blah, until the last element an prime. So the output is ordered. And then look at this. If you look at this short example here, the original input 3141 to 58, after we apply some sorting algorithm onto it, then the output, the desired output, is 26 31 41 in a ascending order. So algorithm is defined as something between the input sequence and the output sequence here, as indicated by the blue arrows here. So what defines the procedures or the operations between the input and output are called algorithms. So given an algorithm, we want to analyze its function and its performance. But when we analyze an algorithm, one of the most important aspects is that if it's correct or not. We say that an algorithm is correct if for every input instance, it will eventually halt with the correct output. So in this case, we say that a correct algorithm solves the original computational problem. And not all algorithms are correct. An incorrect algorithm might halt with an incorrect output, or it may not halt at all. And to the correct algorithms to some problems may not be the correct ones to other problems. And sometimes an incorrect algorithm could also be useful, and as long as we control its error rates under a certain threshold. But within the scope of this course, the correct algorithms are of our primary concern. Okay, so now let's look at some typical problems, real-world problems that can be solved by algorithms. You must be familiar with the term human genome project, which identified all 100,000 genes in human DNA and to determine the sequences of billions of chemical base pairs. So it is so if you view the human DNA as sequence data, then obviously there will be a lot of sequence comparison algorithms or sorting algorithms that are used to compare for example, the similarity between different segments of DNAs, right? And in the realm of internet, so we will have a full range of algorithms to handle massive volume of data. For example, in our routers, there are hardwired algorithms in our routers that try to find the good routes on which the data packets can travel. And whenever you use Google or whatever search engines, the algorithms that are running behind the search engine will find the relevant pages according to your input query as quickly as possible. And in electronic commerce, whenever you create a user profile, you will need to use some password, right, to protect your privacy. So whenever the password is used, some of the most common public key-based encryption algorithms will be used to store the data, to store the password data. And some technology like digital signatures will also be used. And as one of the most popular buzzword in nowadays, blockchain and cryptocurrency, the core techniques in behind those terms are a cryptographic hash algorithm to help build a decentralized networks, to build apps like Bitcoins and so on. Okay. So if we take a closer look at those problems, then we can have more detailed or specified computational problems that are better defined in the language of computer science. So let's look at some of them. For example, the shortest path problem. So it is like given a roadmap on which the distance, all the distance between all pairs of adjacent points, adjacent intersections, or adjacent vertex are known, and the problem is to determine the shortest route from one intersection to another. Okay, so it is one of the most common problems that are faced by the airplane companies. So if you look at this map, for example, the numbers in the circles can represent the destinations, right, or the city names or the country names, and the routes or the edges between the points, between the vertex, they can be a flight route, right? So for example, if this is the background system of a flight company, then given the inputs of the departure city and arrival city, then the system is required to find the shortest route, so that the customers can have as few numbers of stops as possible. This is another problem, which is longest common sequence problems. So it is defined as given two ordered sequences of symbols. For example, X comprises of n symbols from x1 to xn, and another sequence Y is defined as elements from y1 to ym. And the problem is to find the longest common subsequence between x and y. So this kind of problem is very most common in what we have mentioned before, the human DNA data comparison, right? So if X is one segment of DNA segments, and Y is another segment of human DNA, and then such a longest common subsequence algorithm, which returns the longest common parts, can be used as a method to measure the similarity between two segments of DNAs. So here we have a short example here. For example, if X is A to G, A, B, C, D, F, G, and Y is C, D, E, G, H, I, then according to our definition, the longest common subsequence between X and Y is C, D, E, G, because C, D, E, G, they are in both X and Y. Okay, here are more examples of computational problems. A topological sort problem. So this is a problem that you want to design a library of parts, of different parts, and among those parts there are interdependencies. Some part may depend on other parts. And the problem is to sort all the parts so that the parts always appear before any part that depends on it. Okay, so here is a simplified example showing that how the algorithm works. So the upper part here, I'm sorry. So the upper part here is the inputs. This part is the inputs of the algorithm, and it describes the a sequence, all kinds of things you want to do after you get up every day in the morning. So you want to put on your socks, but before you put on your shoes, you need to have your undershorts, your socks put on first, right? So that shows the dependencies between different parts or different events. So it is a like a directed graph data structure. Okay, so the topological sort algorithm will output a graph as shown in part B here. So it always put the events that other parts have a dependency on, because, for example, the socks is sorted as the first one because socks, put on the socks, doesn't have any dependency on other on other events, right? And here the shoes is listed as the fourth position because it depends on, not only depends on socks but also depends on pants, and pants depends on undershorts, and so on. Okay, so the topological sort gives you a way to describe the dependencies between different parts in a system clearly. Another famous problem is convex Hall problem. So it is like given a plane and there are some points on the plane, and the problem is to find the convex a convex Hall of those points. That means to find the smallest convex polygon that contained all the points. Okay, so it may be clearer if I show this graph here. So we have those nails on the plane that represent the points, and the task is to find the smallest convex polygon. That means the indicated by the red lines that include all the nails, all the points within the polygon. Okay, so this is also a common. It has a common application in for example, in the construction plans of the city, or in civil planning, where the points, those nails may represent different sites in the city or different constructions. Okay. Okay, so having seen so many examples of computational problems and the corresponding algorithms that can be used to solve such computational problems, then we want to look at the question of why we need to study the algorithms. As we have mentioned before in one slide, that we care about the correctness, right? And to check whether an algorithm is correct or not is a relatively easy job, an easy task, because we just let the algorithm run once, and if the output is correct, then we say that algorithm is good. And then why do we need to care about more aspects other than the correctness of an algorithm, right? Why do we need to correct? Why we need to care about the efficiency, like how fast the algorithm runs, or how much resources, how much memory resources an algorithm costs? Okay, so the main consideration behind is that although nowadays computers the techniques in computer science develops very quickly, that it seems that the speed of the algorithm, the speed of the computer is no longer a bottleneck. But we always need to remind that computers may be fast, but they are not infinitely fast. And our memory size is also limited, quite limited. The memories are not free memories. So, in one sentence, the computer time is a bounded resource, and so is the memory. Because we have a limit on our resources, we always want to use such resources, no matter it's time or it's memory. We always want to use the resources efficiently. And different algorithms devised to solve the same problem, they often differ dramatically in their efficiency. A carelessly designed algorithm may cost dramatically more resource. It could be more time or could be more memory than a well-defined and a well-designed algorithm. So to showcase the example, we have an example here, which is to compare two sort algorithms. Right. The computational problem is the sorting problem. We want to, given the input sequence, we want to output a sorted sequence that contained all the original elements in the input sequence. So we have two sorting algorithms. The first one is the insertion sort, and we assume that the insertion sort takes that many instructions, which is C1 times n square instructions to sort n items. And the merge sort takes C2 times n times log n, and the base of the log function is 2 instructions to sort n items. So the instructions here, you can imagine it as CPU instructions. That means the lowest level instructions that are processed by the CPUs. So this sentence takes that many instructions to sort n items, means that if you have an input of n items, then this insertion sort will need to use this many CPU instructions to sort an input of n items. Okay, so let's do the comparison of how efficiently insertion sort can compared with the merge sort. Okay, so let's assume that C1, the constant C1 is smaller than C2. And we further assume that we are running the insertion sort algorithm on a very fast computer, let's call it computer A. And assume that computer A can execute 10 billion instructions per second. So this is a very, very, very big number. I'm not sure if nowadays the fastest computer can run that many instructions per second. Okay, so it's just exists in our imagination. Okay, and we also implement the insertion sorts very efficiently in the using low-level programming languages, right? So that the constant C1 is very low. It's just 2. Okay. And we compare with the merge sort, which runs on the very slow computer. Let's call it computer B, which executes 10 million, which is 10 to the power of 7 instructions per second. Okay. And we also implement merge sort algorithm with using high-level programming languages, which is not that efficient, which is not that fast compared with the low-level programming language. So the constant C2 is 50. Okay, and we let them sort the same inputs, which contains 10 million numbers. Okay. So the real time that the computer A takes is 2 times 10 to the power of 7 to the power of 2, because 10 to the power of 7 is the n, is the size of the input, right? And because A runs insertion sort, and C1 is 2 here, C1 is 2, so that's the total. In the denominator is the total number of instructions that is needed to run the insertion sort, right? And on the denominator, 10 to the power of 10 is the speed of computer A. So the running time, the total running time of the insertion sorts on computer A is that many instructions divided by the speed of computer A, which is 20,000 seconds. That means 5-ish hours, 5 or 6 hours, right? And let's look at computer B. The total number of instructions needed by a merge sort, which is C2, which is 50 times n times log n. That's the total number of instructions divided by the speed of computer B, right? It turns out it just takes 1,000 seconds or so, which is 19 minutes, less than 20 minutes, okay? That means computer B runs 17 times faster than computer A on this particular task of sorting an inputs of 10 million elements. And the difference between the speed of the computers, which is the denominator here, the speed of the computer A is 10 to the power of 10, while the speed of computer B is 10 to the power of 7. The difference in their speed becomes irrelevant once we are running a more efficient algorithm on a slower computer, right? Even it's a very slow computer, it's almost 1,000 times slower than A, but because the algorithm is much more efficient than the insertion sorts, merge sort is more efficient. That means the total number of instructions is much lower. So the result is that the total time, the real time needed by the merge sort is much, much slower. So I hope this example shows why we need to design more efficient algorithms, even though we already have very fast computers nowadays. The difference between 5 hours running time on computer A and 20 minutes on computer B is just based on the input of size 10 million elements, right? And you can imagine that if the input size is even bigger, what if we want to sort 100 million or a billion numbers, then the difference in running time could even be larger. And if you're interested, you can do the computation yourself. Okay, so using this example, what I want to say, what we want to conclude is that we should view algorithms as a technology. We should consider it as a technology as important as computer hardware, because the performance of the computer system depends not only on choosing fast hardwares, but also highly depends on choosing the efficient algorithms, choosing the right algorithms to solve the problems. And besides, almost all other computer technologies are directly or indirectly dependent on algorithms. I listed a few examples here, like advanced computer architectures, the design of the architecture of the computers, and the design of the graphical user interfaces, and the software system like object-oriented systems, and the routing algorithms in wired or wireless networks. They are all dependent on the usage of efficient algorithms. And with modern computing technology, you can accomplish some tasks without knowing much about algorithms. But if you have a good background in algorithms, you can do much more. Okay, hopefully so far the slides here answer the question of why we want to study algorithms, why studying algorithms is important. Okay, so it's time for a small quiz. So the quiz is, what is the smallest value of n such that an algorithm in running time 100 times n squared runs faster than an algorithm whose running time is 2 to the power of n on the same machine? Okay, so you can do the similar calculation as I shown in the previous example, and you can submit the answer later in Blackboard, and I will open a Dropbox window in Blackboard. Okay, now let's have a review of the mathematical knowledge that is necessary in this course. First, let's look at the notation of floor and ceiling. So for any real number x, the floor of x is the largest integer less than or equal to x. For example, the floor of 2.9 is 2. And the ceiling of x is the smallest integer greater than or equal to x. For example, the ceiling of 6.1 is 7. Second, the modular arithmetic notation. So for any integer a and any positive integer n, the value a mod n is the remainder or residual of the equation a divided by n, or a over n. In another language, a mod n equals a minus n times the floor of a over n. And it naturally follows that a mod n is greater than 0 and less than n. And if a mod n equals b mod n, we can write a equals b. b is another integer. We write a equals b in brackets mod n. And this equation says that a is equivalent to b modulo n. Next, it's the exponentials notations. So for real number a that is greater than 0 and m and n, we have the following relationships. A to the power of 0 is 1, a to the power of 1 is a, and a to the power of -1 is 1 over a. And a to the power of m to the power of n equals a to the power of the product of m times n, and so on. So here the exponential function is of course a monotonically increasing function with n. And if we use e to denote the base of the natural logarithm function, which is 2.7 to a and so on, we will have that the function e to the power of x can be expanded as 1 plus x plus x squared over the factorial of 2 plus x to the power 3 over the factorial function of 3, and so on. So when I approaches infinity, then the summation of this of this expression equals e to the power of x. So this is the expanded series of this exponential function. And we also have that the limits of this expression, which is 1 plus x over n to the power of n, when n approaches infinity, then the limits of the expression will be e to the power of x. The next mathematical background is the logarithm function. So a logarithm function is defined as follows. For real number b that is greater than 1 and the real number x that is greater than 0, then the log to the base b of x is defined as the number y such that b raised to the power of y equals x. And this log function is a strictly increasing function. That means for a number x1 that is greater than x2, then the log of x1 is also greater than x2. Logarithm functions have a lot of interesting properties. So, for example, the log of 1 is 0, and the log of a product, log c of a times b, is log to the base c of a plus the log c of b. So it converts the product to the summation. And the log b of x to the power of a is a times the log b of x, and it's get rid of the exponential components of a. So here the log function is defined using an arbitrary base b, but in more common situations we want to use a binary logarithm, which is to use the base 2, and a natural logarithm, which uses the base e. But throughout this course, we'll use the base 2 logarithm more often. And another interesting property of logarithm function is that you can change the base to a different constant. For example, the log to the base b of a equals this fraction of log c of a over log c of b. So you can use number 2 to replace c in this expression, so that you can use the binary logarithm to replace a logarithm of arbitrary base b. Another property is that a to the log b of c. So here the exponent is a logarithm, which is the log b of c. And by observing this expression, it means that you can switch c with a, so that the expression on the left equals c to the power of log b of a. And you can prove this by simply take a logarithm of b over on the left term and on the right term. If you take the logarithm on both sides, then according to this property, according to the exponential component property here, you can move the index here. You can remove the index log b of c out, so that you can prove the equality of this equation. Okay, so this is called the changed base of logarithm from one constant to another. This will be a very useful property. So we just mentioned factorial functions a couple of slides before, so let's look at its formal definition here. So for any non-negative integer n, so this is a recursive definition of the factorial function. So when n equals 0, then the factorial of 0 is defined as 1. And when n is greater than 0, and then the definition is n times the factorial function of n minus 1. So this is a recursive definition because there is a explanation symbol involved here, right? So this form is called a recurrence equation. So we will encounter this form of equations a lot. And for simplification, you can just see that the definition of the factorial function is n times n minus 1 times n minus 2 until it reaches the smallest number 1. Okay. Then we will look at some very important functions over a over a set of numbers or a series of numbers. So first, let's look at permutations. So a permutation is a operation on the finite set. Say a finite set S is an ordered sequence of all elements of S. So a permutation is an ordered sequence of all the elements, with each element appearing exactly once. Okay. So for example, if we have a finite set that has 3 elements, A, B, and C, then S will have 6 permutations, which is A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Okay, so each of those 6 permutations is a unique ordered sequence of all the original elements in the set S. So in total, the total number of permutations from a set of n elements is n, the factorial of n. And this you can prove this by thinking of the ways of creating a permutation. Right? We need to choose n elements from the finite set. So when we choose the first element, there is n ways, right? And once we remove that element, then when we choose the second element, there is n minus 1 ways. And then for the third element, there's n minus 2. So if we want to choose n elements, then there will be n factorial, the factorials of n, total number of permutations. Okay. Then another important concept is k permutation of S, which is a smaller subset of the full permutation. So it is a ordered sequence of k elements of S with no element appearing more than once. So we don't choose all n elements, but instead we choose a smaller number k instead of the full range of elements. So for example, in the same finite set S that has 3 elements, then if we want to enumerate all the 6 true permutations, that means we choose 2 elements, then we will have 6 in total, which is AB, BA, AC, CA, BC, and CA. Okay. And the way to compute the total number of k permutations is like this. So when we choose the first element, there is n ways, right? But this time we don't choose all the way down to the last 1 element. We just need to choose k elements. So for the kth element here, there is n minus k plus 1 ways. So the total number of k permutation is n times n minus 1 times n minus 2 until we reached n minus k plus 1. So if we write this term in the form of factorial, then it'll be the factorial of n over the factorials of n minus k. Next, let's meet another important concept, combinations. So a k combination of a set of n elements. So here n set means a set of n elements. Then the k combination is a k subset of S. That means a k combination is a subset of S that has k distinct elements. So from this example, here, if the S has 4 elements, A, B, C, and D, then there are in total 6 2 combinations. So that is AB, AC, AD, BC, BD, and CD. Okay, so all those 6 2 combinations, they have distinct elements from the original set S. As you can see, the difference between K combination with the previous concept, K permutation, is that when we choose a K combinations, when we define the K combinations, then we need to choose K distinct elements from S. And we don't care about the order. We don't care about how the elements in the subsets, how the order look like. Right? The order does not matter here. So its relationship to K permutation is also obvious, because when we choose the K permutation, we also need to consider the ordering, right? Different ordering means different permutations. So for each of those K combinations, it has exactly factorial of K permutations of its own elements, right? So if we consider K elements as a subset, then there are in total factorial of K permutations of this specific subset. Then each of the subsets is a distinct K permutation. Each of those K factorial K permutation is a distinct K permutation of the original set S. So when we want to compute the total number of K combinations from S, we just need to compute the number of K permutations first, and then divide it by the number K, the factorials of K. Okay. Remember how we compute the number of K permutation is this fraction on the right, and the factorial of n over the factorial of n minus k. And then when we compute the K combination, we want to divide by the factorial of K here on the left. So because we want to, we just need to consider distinct elements, but the ordering of those elements does not matter, right? So we want to remove the repeated ordering of the elements. So we write this K combination from elements of n elements. So we can write it within this long parenthesis, long brackets, and we put n over k. Okay, so we sometimes read it as n choose k. And a property of this K combination is that when we choose K elements from n, the number of combinations equals when we choose n minus k elements from n, right? Because there's a one-to-one corresponding relationship, right? Whenever we choose k from n, there's always n minus k many elements left. Okay, so this is the concept of combinations, and both the combination concept and the permutation concept are very useful in analyzing a lot of the algorithms that we will encounter in this course. At last, it will be useful to have a brief review of some of the summation formulas. So first, it's arithmetic series. So the summation from 1 to 2 to n, it'll be 1 over 2 times n plus 1. Okay. And for the summations of squares and cubes, we will also have those equations to describe the summation. Okay, so these equations can be proved through mathematical inductions. And another series that is useful is geometric series. So the summation of 1 plus x squared to x to the power of n. So all the summation of all the polynomial terms of x can be written as the fraction of x to the power of n plus 1 minus 1 over x minus 1. So this summation formula can also be inferred from a mathematical induction method. Okay, so there's a property of this formula. So when absolute value of x is less than 1, when x is either smaller than 1 or greater than -1, then the limit of this formula, of this equation, of this expression, so when n is infinitely big, then x to the power of n plus 1 approaches 0. So this expression becomes 1 over 1 minus x. Okay. So another series that we may use in the future is the harmonic series, which is 1 plus 1 over 2 plus 1 over 3 until 1 over n. So the summation of this term, we don't care too much about the details, but we need to. It's useful to remember that the order of this summation is the logarithm of n. Here the base is the natural base e, and the summation is the logarithm of n plus some constant, and this constant is a rather small number. Okay. And another technique that we may use is that when we have the summation formulas of a series, then we can use the formulas to compute the integration or the differentiating series. So consider a infinite geometric series. Okay, on the left, because it's an infinite geometric series, then we know that the summation is in the form of 1 over 1 minus x. So what if we compute the difference if we want to differentiate both sides of the equations? So on the left, when we compute the derivatives of each item in the series, then it'll be k times x to the power of k minus 1. But now we change the value from we start a value from k equals 1. Okay, so it equals the operation on the left equals operation on the right. We just take derivative with respect to x directly on the right. Then the derivative of the 1 over 1 minus x becomes x over 1 minus x to the power of 2. Okay, so this is a useful trick when you want to compute the summations of a series, a regular series like this, right? By observing the term on the left, you realize that it's just the derivative of the summation on the right. Okay. Okay, for a recap of this lecture, so we first had an overview of the structure of this course, and we gave the definition and we give a short introduction to the concept of algorithms, and through a simple example, we show that why it is important to study algorithms, why efficiency of the algorithms matters. So, and then finally, we had a review of the mathematical knowledge that would be useful in this course. So that's basically the all the content of this first lecture. So now let's spend some time on the grading rules of this course. So homework assignments takes 40%. There will be 4 assignments in total. And there will be a midterm that takes 25%, and a final exam takes 30%. And there will be some random quizzes throughout the whole semester that takes up to 5%. Okay, so as I said, there's no specific programming language required, so all the assignments questions and all the questions in the midterm and final exams are paper-based. You just need to write on papers, or in the homework assignments, you can also write in the Word documents and create the PDF files to submit the homework online or offline if you like. Both ways are okay. So all those deadlines for the homeworks for the 4 assignments will be announced when the problem sets are released. So you will have 2 to 3 weeks for each problem set, and each problem set consists of 5 to 6 questions. And basically, no late submission is allowed, and unless you contact me at least 2 days before the deadline, and you have good reason for a late submission. Okay. So here is a tentative schedule of all topics in this course. So in the first 2 weeks, we'll cover in an introduction and some 2 getting started examples, and we'll cover the topics of the growth of functions. And then we'll spend 3 or 4 weeks on the divide and conquer algorithms and some common sorting algorithms. And then 4 weeks on the dynamic programming and the greedy algorithms. So all those, so here as you can see, the announcement dates, the release date of assignment 1 and assignment 2, they are to be determined yet, because the specific dates will depend on our progress on the topics. Okay, but the timeline is like around week 3 and week 6, and the midterm, the review and the midterm will be around week 7. And then 3 weeks on the graph elements, on the graph algorithms. So maybe I'm considering 3 or 4 weeks on the graph algorithms, because this is a very big topic. Okay, and for the last 2 to 3 weeks, we will talk about NP-completes and the approximation algorithms. Okay, so the final exam will be after the week 15. Okay, so that's it for lecture 1, and from next week, in the lectures of next week, we will talk about we'll start talk about 2 getting started examples using insertion sorts and merge sort to show some basic steps of analyzing algorithms. And hope you like this video, and I will see you next week.